Hello, and thank you for joining me today as we begin our discussion on chemical equilibrium. So first, the idea of equilibrium happens when a reaction takes place and its reverse reaction proceeds at the same rate. So we have kind of two reactions going on, one in the forward direction, one in the reverse direction, and they both happen at the same rate. So for example, in the figure above, we have this substance reacting, and so there's a substance here, which is our initial reactant, initial concentration. And then at this point, things are going in and out and taking place. And then on this one, you will notice that this picture here has reached equilibrium, in which there's equal amounts of forward and reverse reaction happening at the same time. So the idea of equilibrium is that both the forward and reverse reactions are happening, and they're happening at the same time, and they're happening here. And so when you get to equilibrium, the forward and reverse reactions happen at the same rate. So same amount of product is becoming reactant as reactant becoming product. And this happens because both of these reactions are happening. Once you've achieved equilibrium, your amount of product and amount of reactant stays the same. So here we have concentrations, and so this concentration is going to go up, this one's going to go down. We're talking rates. Once we get to our set concentration, notice these lines here are staying the same. So the concentration is not the same, but the concentration is not changing, which means that they are at the same rate, which is what's being shown here. And that's what we're going to talk about with equilibrium. Okay, so for this, when we write equations for equilibrium reactions, we place, instead of drawing just a single arrow, for example, in the past we've done everything as A plus B produces AB. In this case, both this reaction and the reverse, so we're having AB become A plus B at the same time. Okay, so because both forward and reverse reactions are happening at the same time, we use a double arrow instead of a single one. Okay, so anytime you see this double arrow, that means you have some sort of reaction happening that's not complete. It's not a 100% reactants to products reaction. And so we can compare rates, and this is what we're trying to get to again. We want the rate to be the same for both. So for the forward reaction, so in this case we have N2O4 goes to 2NO2, which is what we saw here. So that's where we're getting the reaction from. Okay, so we're using this reaction all the way through. So with this reaction, my forward is going to be N2O4 becoming 2NO2. So my rate law, the rate of this, is equal to Kf, so K, which is your reaction constant in the forward direction, times multiplied by your concentration of N2O4, which is your reactant that's becoming your product. So reactant's becoming product, and so that's where we get our rate law from. Okay, for the reverse reaction, because we're going backwards, we have 2NO2 going to become N2O4. So again, this is going to be your rate constant for the reverse reaction. This is Kr, multiplied by your concentration of NO2, and this one is squared, and that squared comes from this coefficient. So it's a concentration multiplied by your coefficient as the exponent. Okay, and so as we progress through this, when we talk equilibrium, this means that your rate in the forward reaction is equal to your rate of the reverse reaction. So these two rates are going to be equal. So if we take those equations from above, you get Kf, which is your forward constant, multiplied by N2O4 equals Kr, which is your reverse constant, times NO2, and then again this is squared. And so to get rid of these constants, we can solve for them. And so if we solve for Kf over Kr, So I want to get Kf divided by Kr. So right now I have Kf times N2 maybe N2O4 equals Kr times NO2 squared. Okay, if I want to get Kf and Kr together, I can divide and multiply across. I'm going to divide this side by Kr, and I'm going to divide this side by Kr, and then to get rid of the NO4, I'm going to divide by that as well. N2O4, sorry. I'm going to divide this side by N2O4. So I've got my concentrations, or my constants over here, Kf over Kr, and that's going to be equal to, I can cross the Krs off over here, I can cross this off here, NO2 squared concentration divided by N2O4 concentration. That's where this comes from. This is our equilibrium expression. That's what we're going to work with here today. So, continuing on. Where we see this, one place we see this is called the Haber process. And the Haber process is for specifically ammonia. And so this is how we prepare ammonia and how ammonia is created and used. So what happens here is you take nitrogen gas and you add it to hydrogen gas and you produce ammonia. You'll notice these lines here indicate this is a reversible reaction. And so because in this case, my constant depends on stoichiometry. So what we can do to simplify the steps up above in the last slide, what you're going to do is you're going to take your concentration of your products, which in this case is NH3, raised to the exponent, which in this case is a 2, divided by your concentration of the reactants, multiplied together, and then again they are raised to their respective coefficients. So N2 doesn't have a coefficient. We assume 1, so just concentration of N2 multiplied by your concentration of H2 raised to that third power. And a real important piece to this is you notice these are gases. For this process, you're going to have either a gas or an aqueous solution. So it can't be a solid or a liquid. But your gases and aqueous solutions are where we see this take place at. So for a generalized reaction, if you want to write down just a basic general reaction, the lowercase letters are coefficients. The capital letters are substances. And so we have product raised to the product times product raised to the product here, which is the top part of my equation, divided by concentration raised to coefficient divided by, or multiplied by concentration raised to coefficient. So that's how all of those work. In the case that we use a gas, because pressure and concentration are proportional, pressure and concentration are proportional for gases, in a closed system, we can also write this as the pressure of this substance raised to the exponent, and the pressure of this substance raised to the exponent, and same for the A's and the B's. We can use pressures instead of concentration values if they are gases. In a closed system, we can make that happen. Okay, and then so here's a little bit of extrapolation. So we talked a little bit about ideal gas laws. And so PV equals nRT is your ideal gas law. So we can solve for this P because that's our pressure. And so we can divide this by volume and you get nRT over V. Well, this N divided by V is moles divided by volume, which is the same as molarity. And so because of that, we can take your constant multiplied by RT raised to, again, your change in moles. So this is delta N is the moles of gaseous product minus moles of gaseous reactant. And you can end up with this equation for Kp. So your pressure constant can equal your concentration constant times RT raised to the change in number of moles. So that can be done there. And we're going to do some practice with this. So if you're panicking at this point, we'll get there. I promise. Okay, so with equilibrium, because we have forward and reverse reactions, we can get there from either direction. So the ratio of NO2 squared to the concentration of NO2 squared to the concentration of N2O remains constant no matter the initial concentration. So because we end up here, that's our rate, and the ratio is going to stay the same. And that's what we're looking at, is a ratio of products and reactants. So they give you some sample data here, which you can't really see, but we will look at this. I'll show you some examples that you can see. When we're talking K, we're talking our coefficients or our constants. If K is greater than 1, so we took products over reactants, remember? And we're talking concentrations. Concentration of products raised to coefficients. If products is greater than reactants, we have more. K is greater than 1. This comes out to be greater than 1. And they give you a bunch of these to show you if it's a lot bigger than 1. That means your products are going to be mostly present in your final concentration. At equilibrium, your products are going to be found quite heavily. So if you have a K value much larger than 1, your reaction is going to push through. You're going to get a lot of products and very little reactants left. On the flip side, if K is less than 1, and they give you, again, the multiple arrows to show you much less than 1, that means that you're going to have reactants are going to be favored over your products. When we talk about weak acids and weak acids specifically, we're going to get a lot of this K value being less than 1. But this is where your reactants predominate. So not much of your reactants becomes products. So again, K is greater than 1, you have a lot of products here. If K is a lot less than 1, so really small, you have a lot of reactants, very little product. And then the direction of the chemical equation. So this is where we can look at it. So the equilibrium constant of a reaction in the forward direction and the reverse direction are reciprocals of one another. So equilibrium constant, the reverse reaction is the reciprocal of the equilibrium constant in the forward reaction. So what that means is if my reaction is going this way, N2O4 into NO2, 2NO2, we get products concentration over reactant concentration. I'm going to get 0.212 at 100 degrees Celsius. This number is given to you. It's made up. You would calculate this with concentrations here. So just go with, I gave this one to you. Okay. Now, if I want you to calculate my equilibrium constant for the reverse reaction, which is 2NO2 going this way, I can simply take this number and take 1 divided by this. So 1 divided by 0.212 is equal to this 4.72. What this is telling you is that in this reaction, you have a lot of N2O4 and you have very little NO2. Same thing down here, because this is way bigger than 1. We have a lot of product, N2O4, and very little reactant, which is NO2 in this case. But this is equilibrium constants and expressions from there. And this is going to be where we end off. So we'll get through these couple slides and then we'll end off. If we need to find the new equilibrium constant when the reaction has been multiplied by a number, you can just raise your original equilibrium to that power. So to find a new equilibrium constant when the equation has been multiplied by a number, so I'll show you this here down below. You raise your original equilibrium to that power. So here we get stoichiometry coming in. So for example, N2O4 going into NO2, we get this situation and I get 0.212, which I gave you on the last question. Okay, now, if I double my N2O4 and I double my NO2, so again, we raised it or multiplied by a number, I can simply raise my equilibrium constant to that power. So because I doubled it, I can take my constant and square it. And so this is going to be the same as 0.212 squared, would be this Kc value. If I have multiple reactions, and we do a combination here of your Hess's law. We add two reactions together to get our final one. Okay, so when two consecutive equilibria occur, the equations can be added to give a single equilibrium. And then when we do this, our K values are going to be products of the two constants. So for example, I have 2 NOBr goes into 2NO plus Br2. I can also have Br2 plus Cl2 produces 2BrCl. And so we add these two together. And you'll notice that your Br2s fell out. So there's no Br2 on either side. So you get 2NOBr plus Cl2 produces 2NO plus 2BrCl. That's all this. We crossed out our Br2s. In this case, because I'm using Ks, my K3 is going to be K1 times K2. So these are going to be multiplied together, and I'm going to get a final answer of 0.10. That's how you can calculate an unknown equilibria from there. And the last one is heterogeneous versus homogeneous. So a homogeneous equilibria, if we're talking a homogeneous equilibria, we're talking about all the reactants and products being in the same phase. So not necessarily even throughout and all that, we're talking just same phase. So I have all aqueous solutions, they're all aqueous. If I have gases being mixed, they all stay gases. Nothing comes out as a liquid, nothing becomes a solid, they stay gases. They're all in the same phase. If there are multiple phases, we have what's called a heterogeneous equilibria. And so you have multiple substances in different phases. If you have a pure substance, we have a concentration value is always equal to 1, which is going to be real important when we start talking acids and we look at reversible reactions there. That's going to be all for today. I would like you to work through at least the first page of the worksheet, which is titled, I believe it's concentration worksheets here. And so if you go into your homework here in chemistry, and you go down to aqueous solutions and chemical equilibria, this equilibrium constants worksheets, I would like you to do the first page. So just these questions here. There should be 5 of them. There's actually 10. There's 5 on the left and 5 on the right. If you just do the left for now, that's fine. If you can do the left and the right, that means you're sitting really good with this. But that's what I'd like you to do for tomorrow.